This is an example of a second-order transients game in Circuit Tutor on level 2, or the medium level, and we're going to do problem type 2, which would be a parallel LC circuit. You don't actually select this type, it would be randomly determined, but this would be for the parallel LC circuit. So as always, it's a good idea to look at the introductory tutorial before attempting to do the game, and that's especially important for the second-order problems, as they're rather complicated and trying to do them without viewing that tutorial might be rather difficult. Okay, and then it's also a good idea to look at the examples, and again, there's a special interface here for the second-order transient problems that allows you to select what you're going to view, because generating the entire thing could take 2 or 3 minutes. And so this way, if you're viewing an example, you probably want to view all these different times, but you have a choice of whether or not to view the simplification steps at each of those times, which would make it a little bit longer, and the simplified matrix equation. So right now the defaults are not to show any of those details, but if you want to see the details, then you can choose that and then plot it under the options that you choose. So right now I'm going to skip that, and let's do the medium level problem. Okay, so we see that our problem does in fact have a capacitor and inductor that are in parallel here, and then our sought variable is going to be a resistor voltage, which means that the problem is going to be a little more complicated than if the sought variable was, say, the inductor current or the capacitor voltage. So as always, you can give up a course for no penalty if you need to do that and see a complete solution. And we have to solve the circuit at various times, including t equals 0 minus, just before the switch, in this case, opens, at 0 plus, immediately after the switch has done that. Then there's also analysis that's going to have to be done here for the first derivative of the circuit at t equals 0 plus, which is a special thing that you have to do in second-order transients, as discussed in the introductory tutorial. And I would especially recommend reviewing that discussion before trying to do this. And the Thevenin equivalent resistance seen from the combined terminals of the capacitor and the inductor, basically, in other words, between this point and this point in the circuit, having removed those two elements. And then finally, we have to do the analysis at t equals infinity. So we're going to start and go in basically chronological order here. So let's start at t equals 0 minus, which is always the necessary starting point. Okay, so it's been labeled now for 0 minus for our sought variable, and we will need to start out by reconfiguring or redrawing the circuit. In this case, we're going to do that on the screen. If you were doing it on paper, of course, you'd have to redraw the circuit at several different times. So one of the things we have to do here is to change the switches to the appropriate circuit element. So at 0 minus, that's before this switch is open, since it's opening at t equals 0. And therefore this should be a short circuit at that instant. So we can either click on the short here, or if you like, you can right click and change it to a short this way. Either way, that's done. And then on the inductor and capacitor, before we deal with those at this instant, we do know that they're going to be in steady state, because the assumption is that that switch has been closed for a very long time prior to opening at t equals 0. Therefore, any transients in the circuit would have had a chance to die out, and therefore the circuit would have come to steady state by the time we get to 0 minus, is the basic assumption behind all these problems. So that means the inductor will be a short circuit, because V equals L di dt for an inductor, and so if di dt, nothing is changing in time, that's 0, so that means it's going to have 0 voltage and therefore be a 0 valued voltage source, or a short circuit. And the capacitor, being its dual, will be an open circuit, because I equals C dV dt, and therefore if V isn't changing in time, then I is 0, and that means that's an open circuit. But before we can change those, we do need to add additional sought variables. In a second-order problem, you always pretty much need to find the inductor current and the capacitor voltage at 0 minus, because those are the only things that are going to be preserved when we go to 0 plus. Because remember, the resistor voltage can and often does change instantaneously, and so that's not going to be really very useful. So let's add a current here, and we can choose which way it goes. It doesn't really matter. I'm going to choose it to go to the right here. And that's our SOT variable that we need there. Then the capacitor, I want to also add the SOT voltage for that, which is the thing that does not change instantaneously. So I'm going to add by right-clicking. Of course, I get to all these menus by right-clicking on that element after selecting it. And so I can come down to the voltage label and polarity, and I want the plus side. Let's make it on the top so that it'll be sort of the same passive sign convention basically as the inductor. I mean, it's not really related to the inductor current, but I'm just going to use the same sort of convention for everything here. Okay, so we've added those two SOT variables, and we may as well actually just get rid of the V naught of 0 minus. Now you can keep it if you want to, then you'll have to solve for it. I think just to make the problem a little bit simpler, I'm going to get rid of it here because it's only valuable if you want to know what was happening at 0 equals minus. Okay, let's try that again. So the voltage there, I need to make that none. Okay. And now we can go ahead and change the inductor to its equivalent in steady state, which, as I said, is a short circuit. And then the capacitor in steady state we know is an open circuit. Now we can't just delete that with the delete key because then we wouldn't have the SOT voltage anymore, and it really won't let you do that. So instead we're going to use the terminals because those are needed in order to be able to show the SOT voltage, just in terms of how we draw the diagram. Okay, so we've basically done everything we need to do here for the switch and the reactive elements. And so we're done reconfiguring the circuit. And if you did make a mistake there, you can always click Restore Circuit at any point. Okay, so now let's inspect what we need to find. Well, this capacitor voltage, that's going to be very easy because we see wires connecting both sides, so that clearly has to be 0. Now for the inductor current, that's maybe not quite as obvious because we do have a source in the circuit. So let's go ahead and do a little bit of simplification of the circuit to make things easier. So I'm going to see that I first of all have two resistors in series, so the 8 ohm and the 7 ohm. That can clearly be combined into a 15 ohm resistor. And then I change the other one to a short so that the total resistance is still 15 ohms. So that just makes things a little bit easier. So we'll check that combination, and that's valid. Now let's see, what else can I do? So one other thing I could notice here is that this 4 ohm resistor is actually shorted by this wire. And therefore it can't have any current because it has 0 voltage by Ohm's law. And therefore it's not going to affect this current since it has no current anyway. So we may as well just delete that since it's a shorted element. I'm just going to hit the delete key, and that gets rid of that shorted element, which helps simplify the circuit a little bit. Now I'm going to inspect here a little bit more, and nothing else is shorted or dangling. So that's probably all I'm going to be able to do. I can't do a source transformation because of this SOT current, so I won't try to do that. That would prevent it because that basically would get lost in the shuffle if we try to do a source transformation. So I'm done editing. And I've simplified the circuit now down to where it has, say, for example, 2 meshes. And the number of nodes here, well, I basically have 1 node here, 1 node here. So being a single node pair circuit, I might want to just choose that. Okay. Okay, so it's not going to allow me to do this because the capacitor basically is shorted, and the program can't handle that situation. So what we can do, we could do nodal analysis, and that's what we'll basically have to do instead. So this is just a technical issue with the program. So I'm going to just take this great big node and make that our ground. And now we'll treat it as we're doing a normal nodal analysis. So let's see. First of all, I could just dispense with this SOT voltage since the value of that is quite obvious. So let's select SOT branch voltage. So BC of 0 minus. Because that's shorted, we know that has to be 0 regardless of anything else. I may as well just take care of that first. Okay, so that's done. But again, this we don't know what that's going to be. That's basically the current through this 2 ohm resistor. If you look at it, it really is a current divider circuit in the sense that the current from the 2 amp is splitting up between this resistor and between this resistor. I don't think, however, because of the SOT voltage, it's going to let me select that, but let's just check here. SOT branch current. No, it's not letting me select that. So I'm going to have to basically just do a conventional nodal analysis. So let's do a KCL equation then. Let's do it for node 1, which is our only non-reference node, so that won't be very hard. And we have the current through the 15 ohm resistor, so that'll just be 1 voltage, and then through the 2 ohm is the same thing. And then the 2 amp source, oops, I have to click that again, and the 2 amp source, and then that's going to sum up to 0. So basically through the 15 ohm I have V1 over 15 ohms, and then I have V1 over 2 ohms, it's going to be that second current. And then the third current leaving node 1 would be the 2 amps through that source. So that'd be plus 2 amps, again, because all those currents, all three of those are the currents leaving node 1. So we'll check that, and that is correct. And that's basically equivalent to doing a current divider. And let's see, then I need to have the current through the shorted inductor here. So that basically is just going to be whatever current goes through here, it has to also go through that, and so that'll allow me to get that very easily. So that's just going to be V1 divided by, V1 divided by 2 ohms, because since this is an open circuit, whatever goes through here has to also go through here, and in the same direction too. So that has the correct polarity for a current going in this direction. So I don't have need to have a minus sign there. So we'll check that. Oh, I typed the wrong thing there. I typed V2 and I meant V1. I think I typed the 2 there by mistake. That's what happened. So anyway, check that again. V1 over 2. So that's what I meant to put in. Okay, and now I think that should be it as far as our equations are concerned. And so now it just wants us to basically put this into a single form. And so the V1, I could just do the calculation. That's 1/15 plus 1/2. So if I just put that on a calculator here, that would be 1/15 plus 1/2 would give me 0.5667 times V1. And then over on the right-hand side, I bring this constant over the right, and that's going to give me the -2 there. Okay. And you, of course, won't have the cheat button there, but that just helped speed that up for me a little bit. So we'll check that now. And that's our simplified equation. It's just one equation and one unknown, so very simple. And now I just have to divide to get the numerical value, which will be -2 divided by 0.5667, so that will be -3.529. Just again using a calculator for that, and we'll check that, and that is correct. And then finally we need to find, we've already found VC of 0 minus, that's dimmed out, so we don't need to enter that, and we can't enter it actually. And the IL minus, that's going to be the V1, which we just computed, which is the -3.529 divided by 2. So just doing that division then, that will give me -1.765 amperes for IL of 0 minus. So let's check that. And that is correct. Okay, so that completes the analysis at 0 minus, and the results have been summarized here for us for reference in the future. And now, next step would be to analyze the circuit at 0 plus. So I'll click on that button. And you notice that's changed the labeling here to indicate everything at time 0 plus. So if you're doing that by hand on paper, you would need to redraw the circuit in this way. And then, of course, you'd also be doing what we call reconfiguring on paper just right away. But here we're going to do that on the screen. So we go into the special restricted reconfiguration mode, and let's first of all deal with the switch, because that always has to be changed in a reconfiguration mode. And now, because that switch is opening at t = 0, that means it should now be an open circuit since we're at 0 plus, which is after t = 0. And so I'm just going to hit the delete key there, and that gets rid of that and its associated wires. Okay, so we've taken care of the switch, and now we need to think about the inductor. And so what do we know about that inductor? Well, we know IL of 0 minus was -1.765 amps. And remember, for inductors, current cannot change suddenly through an inductor. That's because V equals L di dt, and a sudden di dt would be infinite, basically, and that would get infinite voltage, which is not allowed. So this same current has to apply at 0 plus. So basically that means that this basically should be a current source with that value. Now that's with IL pointing to the right, as indicated here. Since it's a negative value, I'm actually going to make it point to the left. So I'm going to replace it, since I know it's current, I can replace it by a current source, because that current source has, by definition, a fixed current. So that's going to be, and actually that's going to be a plus 1.765. And the reason it's positive is because I have changed the direction of the source with respect to the original value, so that makes the negative positive. That's just to avoid having a negative sign in my source value. Okay, now before I finish with that though, I have to remember that I also need additional SOT variables in a second order circuit. In other words, you always need to know, you're going to have to find out basically the first derivative of this inductor current, and that depends basically on the inductor voltage, because remember VL equals L DIL dt. So the DIL dt is what we're after, so that's going to be VL divided by L. So therefore I have to define a SOT voltage on here, and I'm going to do that with passive sign convention with respect to the direction of that current source now. And so I'm going to put positive sign on the right. I think that's probably the easiest way to do it here, rather than respecting the original convention, because since I've already reversed this, I'll reverse this as well. Okay, so now we have passive sign convention for that element. Now, for the capacitor, say, what do we know about the capacitor? Well, we know that VC at 0 minus was 0 volts. Well, we know that for a capacitor being the dual of the inductor, its voltage cannot change instantaneously, because I equals C dV dt. And therefore, that would produce an infinite current if the voltage were to change suddenly. So this is also VC of 0 plus. And if it's 0 volts, that means basically that's going to be the equivalent of a short circuit. So I'm going to basically need to change this to a short circuit. But before I do that, I need to add a SOT current, because again, the SOT current of the capacitor is going to be necessary to find the dV dt of the capacitor at 0 plus, which is necessary to solve the second order circuit. Because remember, I need a second basic initial condition. So I'm going to right click there and add a current going down in passive sign convention with respect to the SOT voltage. And then I can change that, now having added the SOT variable. I can't add that after I change it to a short, just because it doesn't allow you to add currents to shorts. So now we can change it to a short. And now we basically have properly treated the capacitor and the inductor and created the two SOT variables that we need to solve for, namely VL and IC. So they're sort of the opposite of what you do at 0 minus, where you found VC and IL. Okay, and then we still need this V naught of 0 plus. That's what we're basically trying to find in this circuit. So we're done reconfiguring now. And now think about how I could go about simplifying this circuit. So this one is a little bit tricky. I need to solve for all these variables, and some of them, you notice that the circuit actually is hinged here by this wire that goes across. That basically isolates everything on the left from everything on the right, which is just the current source. Or in other words, you could also think of that as just shorting the current source. But the problem is that we want to know the current through that wire. So therefore, nothing is removably hinged here, and besides which we have SOT variables on both sides. So we can't simplify this hinged situation. Now, one thing we can do is just combine these resistors in series. So let's just go ahead and do that, which will make our problem a little bit easier. So we'll just make that the 15 ohms and change this one to a short. So that gets rid of one circuit element that we don't have to worry about anymore. Now, you might say, well, the 15 ohm is in parallel with the 2 ohm because they're connected on both ends. But the problem with that is we cannot combine those, because that would affect this current, right, that's going through the wire to the 15 ohm. So because that would be affected, we're not allowed, they're not basically something that we can combine without affecting the SOT variables. Remember, you can never make changes that will affect the SOT variables, so we're not allowed to combine those in parallel in this instance. One thing we can do, however, is you notice that here we have a 4 ohm resistor, and if you have sharp eyes, you might notice that that's actually in series with a 2 amp source. And remember that if an element is in series with a current source, That's basically what we call a redundant element, because that current is going to be 2 amps no matter what this resistor value is. And so it really is not playing any role except in determining the voltage and the power of this current source. But we're not interested in either of those two things. So we can basically just change this to a short, allow the current to continue to exist there, but that'll simplify. And so they call it removably current splittable. That's the same thing as redundant in this case. It's just made redundant by one current source. Okay, so that's simplified things a little bit. And now we can't remove the current source even though it is shorted because once again we need this current and we need this voltage, so we're not allowed to do that. So we basically have done everything that we really can do here. Okay, so now we can look at this circuit and say, well, we've got one node there and we've got one other great big node here. So this is really a single node pair circuit, although it might not look like it at first glance. So we could treat this with single node pair analysis. That would probably be the easiest way because it would have multiple meshes and that would be probably a little more complicated. Oh, and again, it doesn't allow you to do that when you've got a shorted current source. So we'll have to treat that as actually nodal analysis. So I'll select nodal analysis, and then I'll put my ground here on this great big node. Keep things simple. So as before, we have to do the nodal analysis, and so now let's do, similar to what we did before, we'll do a KCL equation for node 1 here. And so we still have the current through the 15 ohm, we have the current through the 2 ohm, which will need a form like that since that goes to ground, and then the 2 amp source will be that, and all that will equal 0. So that's the terms that I need, and I'll just fill in the blanks here. So this is going to be V1, and I'm going to use the tab key here to fill in more quickly, V1 divided by 15. And we could also have V1 divided by 2, or you could have actually combined those two resistors in parallel and put one value here if you like and just use one term, but this is probably just as easy. And here we have a 2 amp source there. Again, all those currents are leaving this node, and so that has a plus sign there. Again, you always have to watch out for polarity anytime you're dealing with a source like that. So that is correct. And now we have 3 SOT variables, so we need to write some SOT variable equations. So let's go ahead and do some voltages first. So the voltage across this inductor, which is represented by the current source now, we see that's obviously 0 because it's connected by wires. So that voltage has to be 0. So we just say that that's equal to 0. We don't need to do anything further. And just check that. And then the other voltage we're interested in is the one across the 2 ohm resistor. And that basically is just synonymous with V1 because it's V1 minus ground, which is 0. So that's just equal to V1. Very simple. And then we need to also do a SOT current here, because we have one of those through that wire. And getting that SOT current now, that's a little bit tricky because basically what we have to do is we have to find, we have to apply KCL due to this sort of portion of a node, basically. In other words, we could draw a closed surface here around this right here that I'm outlining, and we could apply KCL to that closed surface. So basically we're going to add the currents that are leaving that closed surface. And so let's just do it that way to be clear. So we have a current leaving through the 2 amp source, which I'll represent that way. We have a current leaving through this source, which I'll just add a separate term for that. We have the IC of 0 plus, which is leaving. And then we have through the 2 ohm, we have basically a term like this. And we can set that all equal to 0. This might be the easier way to understand it. So the current leaving through the 2 amp is actually negative 2 amps because the 2 amp source, the current is flowing into this, again, closed surface that I'm drawing right here. And then this one, again, would be also negative for the same reason, that that current is actually flowing in. So that would be 1.765. Oops, sorry. 1.765. And we could just add those together mentally and put one term in, but it doesn't matter. And then the IC of 0 plus, that's a plus sign because that's also leaving this closed surface. And then I want the current going this way through the 2 ohm resistor to the left, because again, that would be leaving this closed surface that I'm drawing here. And so that would be negative V1 divided by the 2 ohms. And again, that's because the voltage we come from is 0 and we're going to V1, so 0 minus V1 is negative V1 divided by 2 ohms. So that's an equation, sort of an indirect one for IC of 0 plus. Now, if you like, you could then maybe solve it before we even enter it. And so I could do that by basically removing the 0, put this on the other side and make it a plus. And then I could put this on the other side and make that a plus. And I could put this on the other side and make that a plus. So I can just do algebra here, and that way I've solved a little bit more directly for that. And you don't have to do that, but it's just, I just thought I would do that. And now we basically have everything we need. So we'll click no more equations. And now basically it wants us to form the equation here. So once again, we'd say 1/15 plus 1/2. That's going to be 0.5667. Basically, the 0.0667 is 1/15, and then the 1/2, of course, is 0.5. And then I have the 2 brought over to the right-hand side again, negative 2. So we'll check that, and that is correct. And then we just have to solve for V1 here by dividing by this coefficient. And so on a calculator, negative 2 divided by 0.5667 would be negative 3.529. And we've already found VL of 0 plus, that's dimmed out, but the other quantities V naught of 0 plus, basically we go up here, and that's just equal to V1. So we know that V1 is negative 3.529 volts, so we just put that in there. And then the IC of 0 minus, that basically is V1, this value, divided by 2, plus this, plus this. And if you do that arithmetic on a calculator, then that works out to exactly 2 amps. So we'll check that. And we've now completed the calculation at 0 plus. However, we're not done with 0 plus yet, because we also need to analyze. In other words, this gives us one initial condition for V naught at 0 plus, but we also need to know V naught prime, because that is our sought variable we're trying to solve for here. The others were just sort of auxiliary things that we're using to solve for the thing that we really want, which is this resistor voltage. So we're also going to need, because it's a second-order differential equation, we're going to need V naught prime at 0 plus. That's where this first derivative circuit comes into play. And so I'm going to analyze at the same instant of time, but now I'm going to analyze what we call the first derivative circuit. And again, it's very good to read about that in the tutorial, since that idea is different from what the way a lot of textbooks do it. Okay, so I have to reconfigure the circuit again at 0 plus, but now I'm basically forming the first derivative of this circuit. So what that means is that every voltage and current in the circuit is not really a voltage and current, it's actually the first derivative of the corresponding voltage or current. So in other words, it would be volts per second or amps per second, because that's the units of the derivative quantity. So we have to think about how to analyze this. The switch might be the easiest place to start, because we know the switch is still open at 0 plus, so we can just delete that as I did before. So that's done. And now, and remember, we can't simplify yet. We just have to reconfigure here. We're not allowed to simplify in this mode. So now, again, to form the first derivative here, we remember that the first derivative of a DC source, since it has a constant value, its first derivative with respect to time is actually 0. And that means this can be replaced by a 0 value current source, or just an open circuit. So I'm going to delete the current source. That's what it's talking about, source killing being required. Now, if I had a voltage source here, again, the time derivative of that would be, again, 0. So that would become a short circuit rather than an open circuit. Okay. So we've taken care of that source. Resistors are going to stay all the same, and that's because if V equals IR, then if you differentiate that, it says V prime is equal to I prime R. And so it obeys basically the same Ohm's law for the first derivative of the voltage and current as the voltage and current themselves do. And so that means resistance values, nothing happens to those. They stay the same. What we do need to change would be the inductor and the capacitor. So the inductor, let's think about what we know about this. We first of all know that at 0 plus, the inductor voltage is 0. We've already figured that out in the last step. Well, remember that voltage, VL, is equal to L dIL dt. And dIL dt, therefore, is now known to be 0. Okay, because this voltage is 0. So di dt has to be 0 as well for any finite value of inductance. So since di dt is 0, that means that this basically is a 0-valued current source. And that means it's equivalent to an open circuit. Now I can't just delete it because, or no, wait a minute, I'm sorry. No, that's right, because at 0 plus I need to find the first derivative of this voltage, and that's going to be, no, I'm sorry, we're at the first derivative circuit. I take that back. We don't need to do that. So this we can just basically change to an open circuit. So it's a 0-value current source, so I just delete that. Okay. And then the capacitor, now what do we know about that? We know that it has a current of 2 amps. Well, again, IC equals C dV dt. So what we know is we know it's dV dt because that's equal to this value, the 2 amps, divided by the capacitance. So 2 amps divided by 2 farads would be 1, and then that would be the 1 volt per second. Okay, because that's what the units work out to. So this is going to be a voltage source, and again we had IC pointing down, so consistent with passive sign convention, that means we want to put the positive side of the voltage source on the top. So our voltage source, I need to reverse its polarity from the default here, and then again it's going to have 1 volt per second because that's the value of its current divided by its capacitance, which gives me the dV dt. And again, this is dV dt, we know that because it's showing units of volts per second here. This is the first derivative of the original circuit. Okay, so we've done everything we need to do here. So we're done reconfiguring the circuit for the first derivative calculation. And now clearly it would be advantageous to simplify this a little bit. So we've got a dangling resistor there, so I'm going to go into the simplification mode in the circuit editor, and I can get rid of that dangling 4 ohm because that doesn't contribute anything to the circuit. And then I might also just go ahead and combine these 2 series resistors again and make 15 ohms out of that and change that to a short and check that combination. And now we probably recognize that you have basically a voltage divider. So in these first derivative circuits, all the normal circuit analysis techniques work just the same. It's just you're dealing with derivatives of things. So basically we're done simplifying that. So I'll exit the circuit editor, saving those changes. And now, because it's a single loop, we can treat a voltage divider very conveniently in a single loop circuit. So I'm going to choose a SOT branch voltage so that I can use the voltage divider formula, which is here. So my V0 prime of 0 plus, which is this SOT variable, that is going to be equal to something I can determine using this standard voltage divider formula. Now notice here that this is the voltage in volts per second because this is actually the first derivative, just as this is the first derivative. So that value is going to be 1 volt per second. But then I have to check polarity as always. So here the positive side is connected to the negative side of my SOT voltage and the negative to the positive side, so I do indeed need a minus sign there. So I have to be very careful always about polarity. Now remember, in a voltage divider, the voltage of interest is across the, that's the resistor you put in the numerator, which is the 2 ohm. And then we put that there, and we also put the 15 ohm in the denominator. So that's the standard way the voltage divider formula works. And remember that this voltage, or voltage per second really, divided by the resistance, that's the current, and then the current multiplied by the 2 ohm gives us this voltage. That's why the formula looks the way it does. Okay, so we check that, and that's all we need here. So now we're just going to do the numerical calculation on the calculator. So that's basically just negative 2 over 17. So that works out to be negative 0.1176, again, volts per second. And that is correct. And basically, that's what we needed, was this V0 prime at 0 plus. So now we have a couple more tasks. We have to find the Thevenin equivalent resistance from the terminals of the combined inductor and capacitor, because that's how we originally derived the form of the transient solution. So click on Find RTH, and so now we're going to go into the reconfiguration mode again. And now we want to reconfigure it to find RTH seen from the terminals of those elements. And we're doing this, remember, at t greater than 0, because that's when the transient that we're trying to find is taking place. We're not interested in RTH at t less than 0, so we have to assume that t is greater than 0. And what that means in practice is, of course, that the switch now is going to be open rather than closed. So I have to delete the switch, as I've been doing in all the other cases at t greater than 0. Okay, now I also don't need any sought voltage here, since we're only finding resistance, and it'll actually complain if you don't delete that. So let's go ahead and just get rid of that sought voltage by right-clicking there and setting that to none. And then I need to basically turn one of these two things into terminals, and then the other one is going to become an open circuit. It doesn't matter which one I pick. It'll accept it either way, because either way you're going to be able to basically view what you're seeing from between this terminal and this terminal. So say maybe I'll change this one to terminals. Okay, then the other one would be deleted so that it's not shorting it out, and so that I'm seeing now what the combined inductor and capacitor see in the rest of the circuit. Okay, so I could have done it the other way. Doesn't matter. The result will be the same. Now the last thing I can do here is to kill the independent sources, because since I'm finding R Thevenin, remember that when you find R Thevenin, you always need to kill all of the independent sources, which is the only kind we have in this problem. So that means the 2 amps basically needs to be turned to an open circuit, or I'm just going to delete it. I don't have to do that in this mode, but I can, and it'll just save time. So I'm going to go ahead and do that now. Okay, so that basically does everything I can do in this mode. And I could go back into the circuit editor now to simplify this, but really I don't probably need to do that, because I can see that this is dangling and doesn't play any role. And since these other 3 are all in series, I can just add their values mentally. So I'm just going to go ahead and enter that value. It's going to be 7 plus 8, which is 15, plus 2 is 17. So I'm just going to enter 17 ohms. So you don't have to use the circuit editor here if you don't want to. And that's correct. And again, the 4 ohm didn't play any role there because it was dangling. Okay, so it's just putting our progress. Now the last part of the calculation we have to do before we find the transient is to analyze at t equals infinity. So I'll click there. And once again, it's going to change the labeling to be t equals infinity, and this is something you would do on paper if you were doing it manually. And then I go into reconfigure the circuit, which is something, again, you would just do on paper if you were doing it that way. And now, because I'm at t equals infinity, the switch clearly, again, it's greater than t equals 0, so that switch is going to be open. And so I delete the switch, as I did before. Now, this is my sought variable, so I'll leave that alone. And of course, I don't kill sources here because I need to know what the voltage is, and that's going to be caused by the source. I do, however, need to change the inductor and capacitor into more appropriate things. So you have to remember that at t equals infinity, any transients that were present in a stable circuit will have died out. And that means that we're going to be, once again, in steady state, just like we were at t equals 0 minus. So that means in steady state, remember, an inductor is a short circuit, so I'm going to change that to a short. And the capacitor is an open circuit, so in this case, I can just delete it since I don't need its voltage. Okay, so basically, that's all the reconfiguration that we need. Now, we're not allowed to simplify in this mode. And so now to do this analysis, it might help to simplify the circuit a little bit. So I'm going to go into the simplification mode. And this circuit's actually a lot simpler than it looks. But basically, I can combine these 2 resistors in series. So that'll give just 15 ohms, as I've done before. Check that combination. And now you might observe that these two resistors are in parallel, the 15 ohm and the 2 ohm. Now, it does have a sought voltage here, but will that affect it? And a moment's reflection should tell you that that will not affect anything to combine those in parallel because they both have the same voltage already. So that's perfectly permissible here. Now, if it was a sought current through the 2 ohm, then that would not be permissible without, say, doing a sought variable transformation or something, which actually is not even allowed here. So I'm going to just replace that by the product over the sum, which would be 2 times 15 divided by 2 plus 15. So that's going to be 30/17, which works out to 1.765 in decimal form. And then I delete the other resistor, and I check that combination, and that is in fact correct. Now, if I wanted to, I could notice also that this resistor is redundant with respect to the 2 amp source. So possibly I could just change that to a short if I like. I don't have to because it's really not necessary because the current's going to be the same either way, but yeah, may as well. So now we've simplified as much as we can. So we're done editing. And again, that was redundant because it was in series with the current source. And if you left it there, it's not going to make any difference anyway. So it doesn't really matter whether you removed it or not. So now we have basically either a single node pair or a single loop. It doesn't really matter very much. We call it a single loop. And so I want a sought branch voltage, and now I could just use Ohm's law, and so that's going to be a current times the resistance, since the current fixed current is going through that resistor. So I'll just use this term. If I wanted to, I could just calculate the number right away and put it in here. That's another option as a voltage. I'll just do it this way, I guess. So let's put in 2 amps. And now we have to be very careful to observe that the gotcha with Ohm's law, of course, is always polarity. So here the current is going into the negative side of my sought voltage. So that means this is going to be active sign convention. So I have my 1.765 ohms, but I must have a minus sign here because of active sign convention, the current going into the negative side of the sought voltage. So that's the important thing there. Okay, so we'll check that, and that is correct. And that's all the equations we need. So now we just basically need to do that math, multiply 2 times 1.765 or negative 2 times 1.765, and that will give us negative 3.53. So we'll check that, and that is the value. And now we're just waiting for a summary here. So we've done basically all the calculations we need to do to find the transient formula, but we need to just wait for a moment here. Okay, so here's all our results summarized. Now you wouldn't see this part at the bottom. That's actually only shown to instructors. That's kind of for cheating, but we won't use that here. Okay, so the only type of equation to select is second order transient, so we'll do that, and it is going to pop up a little cheat sheet here that has all the relevant formulas that you would need in a second order transient problem. You have to select the appropriate ones, however. And let's go ahead and start forming the expression for V naught of t, which is our sought variable. So we'll just put the sought variable there, equals. And then first of all, we have to think, well, do we need a constant voltage term? We obviously don't need constant current or constant power because those have the wrong units to be a voltage. So we might need this term. We have to look and see, well, what is V naught of t equals infinity? That's the particular solution, or the forced solution. And indeed, that is not 0 here, so we do need that term. And again, that's kind of part of the general solution here would be this particular solution, and this is assuming constant sources. All of these, well, these formulas at least are assuming constant sources. So we'll put in that negative 3.53 there. And so we have that part done. And now we also need a transient term, of course, because this is a transient problem, unless its coefficient happened to come out to 0, and that won't really happen here. So we have just a simple exponential decay, and that would be appropriate if you're overdamped. You'd need 2 of those. If you're critically damped, you need one of these, and you would also need one of these terms that has the t prefactor in front of the exponential. So t e to the negative t over tau. That's for critical damping. And then this third form is used by itself because it's actually equivalent to two terms, and that is the underdamped solution. That's going to be the one that exhibits ringing. So how do we know which of those we need? Well, we have to determine the type of damping. And that means we need to evaluate zeta using the formula indicated here. So this is a parallel parallel LC circuit. So, and here it's called G Thevenin CL. And here's the value of zeta. So I'm basically going to take that, and now I'm going to pull up some algebra I've done here ahead of time. So first of all, let's find that G Thevenin. So remember that R Thevenin is just 1 over G Thevenin, or G Thevenin is 1 over R Thevenin. So we just take the reciprocal of 17 ohms, and using a calculator, that works out to 0.05882 Siemens now. And then I can plug that into my expression for my zeta to determine what type of damping the circuit has. So I'm going to take my G Thevenin here, divide that by 2, so that's 0.05882 divided by 2. And then I have the square root of my L over C. Remember that the L here was 7 henries, and the C was 2 farads, so we put those numbers in, and then just evaluate that on a calculator, and that works out to 0.05502, which is obviously less than 1. It's quite a bit less than 1. And therefore, since the damping factor measures the amount of damping in the circuit, this is clearly underdamped. Remember, critically damped is when zeta equals 1, and anything less than that is called underdamped. Anything greater is called overdamped because there's more damping. So being an underdamped circuit, I know right away which of these terms I'm going to need actually. I could go ahead and just click on this one for my transient term. Is going to be that underdamped term. And basically, this form is valid in all cases except for the critically damped case where you have to put in the extra factor of t here. But for anything that's not critically damped, this would be the valid form. But when I'm underdamped, basically, I know that my complex frequencies are going to become complex. So remember the complex frequencies, if I take this trial solution, k e to the s1t, or just k e to the st, for example, put that into the original differential equation, which is not written here, and turn the crank, basically, I would get that the characteristic equation would have these roots, that S1 and S2 are given by negative omega naught times zeta minus plus the square root of zeta squared minus 1. So because we have zeta squared minus 1, since zeta is less than 1, that means obviously zeta squared is going to be less than 1, and therefore this is going to be the square root of a negative number, so this is going to be imaginary, and therefore the frequencies are going to be complex in nature. And they're in fact going to be a complex conjugate pair, as they always have to be. Okay, so to evaluate these values, I'm going to find my omega naught first. That's always given by 1 over the square root of LC, be it a series or parallel circuit, because the dual of one is just involves changing L to C and C to L, and that doesn't change this formula, so that's valid in both cases. So I have 1 over the square root of my 7 henries times my 2 farads. Evaluating that on a calculator, that gives me 0.2673 radians per second. And again, you can work out the units as shown here to confirm that is in fact radians per second. Now that's my undamped natural frequency. My damped natural frequency, which I also need, that's given by this formula, which is omega naught times the square root of 1 minus zeta squared. Okay, so that's basically what happens when you factor minus 1 out of this square root to give you a j. So we put an omega naught there, that's the 0.2673 radians per second, square root of 1 minus zeta squared. Remember the zeta was up here, I'm sorry, it was up here. This is zeta, that's R Thevenin, or sorry, that's G Thevenin. So put that number in there, square it, and then evaluate that, and that comes out to be just a little bit less than omega naught because the damping is quite small in the circuit, so it's 0.2669 radians per second. So that's my omega d. Now, other parameters that I will need in an underdamped case are this sigma, which is going to be basically the real part of the, or negative sigma rather, is the real part of the complex frequencies. So sigma is defined as zeta times omega naught. So I just do that math. The zeta is the 0.05502 times the omega naught, which was up here, the 0.2673 radians per second. Again, don't get that confused with omega d because those are different numbers. You know, they're rather close here, but they're not the same. And so multiplying those two together, that gives me mathematically on a calculator 0.01471, and I'm calling that nepers per second. Now you say, well, it's radians per second, but because this is now in a real exponential, it's normally called a nepper rather than a radian. even though omega would be called a radian. Okay, so now the time constant that appears in this formula here, for example, the denominator, that's basically the reciprocal of the sigma, because it's e to the minus sigma t or e to the negative t over tau. You could write it either way, like this, or like down here, for example. So the tau is the reciprocal of sigma, and that's 1 over the 0.01471 nepers per second, so that will work out to almost exactly 68 seconds. And our complex frequencies, we don't have to actually enter those here, but it's negative sigma plus or minus j squared minus 1 times omega d. Now, again, the original form of V naught of t would be this form that applies in everything except critically damped cases. But using Euler's identity, because the S1 and S2 are complex conjugates, it's very convenient to use this form here and then apply Euler's identity to the complex exponential. So we'd factor out the e to the negative sigma t, which comes from the real part of the S1 and S2, and that comes out of both terms. And then we would basically replace the e to the j omega plus or minus j omega dt by the Euler identity correspondence, which would be cosine omega dt plus or minus j times sine of omega dt. And having done that, then I can regroup. I'm going to have actually 4 terms. But when I regroup them, I can combine them into 2 terms where I have a1, which is a new constant, cosine omega dt, plus a2, sine omega dt. And here, the a1 is just the original k1 plus k2, and the a2 is j times k1 minus k2. So the a1 and a2 are now going to be real numbers, whereas the original coefficients, the k1 and k2, actually had to be complex in this case in order to keep the voltage as a real number. And then I also need to make sure I don't forget now the particular solution, because that was not 0, remember, in this problem, so we have to retain that. So now, applying the first initial condition is the value of V naught at 0 plus. So remember that we had determined that that was up here negative 0.3529 volts. So that's equal to this evaluated when t was equal to 0. So the exponential becomes e to the 0, since t is 0, so that's just 1, so that goes away basically. And then the sine of 0, as you know, will be 0, so that this term goes away entirely. And then the cosine of 0, as you know from drawing the unit circle, is 1, so that's the x-coordinate on the unit circle. So that basically just leaves us with nothing but a1 here. But we also have the particular solution, which we must not forget, and that's the V naught of infinity, because remember, that's not 0 here. So that's what's equal to this. And the V naught of infinity, interestingly, happened to also be negative 3.529 in this case. So plugging that into here, we see then that solving for a1 just gives us a1 equals 0, actually. And so in this case, the a1 is identically 0. Now to solve for a2, that's where we have to use our second initial condition, which is the V naught prime at 0 plus. So first we have to find an expression for V naught prime, which we do by differentiating this form of the equation. Now we could go down to this second form here, which is this single cosine, and do that. But I think it's actually a little bit easier to use this form when you're applying the initial conditions. So that's why I'm using this form rather than going all the way down here. If you want to try doing it down there, you can, but you may find it would have actually been easier to do it up here. So I'm going to just stick with that form before we've actually transformed it into this additional form, which is discussed in the introductory tutorial. So we take the derivative of this, and so first let's notice we have a product of functions here. We have the exponential times either cosine or a sine. So there, we have to use the product rule, and we also have to, of course, use the chain rule because there are coefficients multiplying t inside each of these functions. So using the product rule, let's first differentiate this, and that brings down the negative sigma in front times e to the negative sigma t, and then we just copy this because that's not being differentiated now. And then the next term, then we have this not being differentiated times the derivative of this, according to the product rule. And so the derivative of cosine omega dt will be negative omega d times sine omega dt, and then we still have the a1 coefficient. And then the derivative of sine of omega dt, again using the chain rule, that brings an omega d out front, and then it's going to be plus cosine omega dt, and then we of course also have the coefficient a2. Now the derivative of this term, because that's a constant, that's just 0, so that goes away in the derivative expression. And we're just left with these 4 terms here. And now we need to evaluate this at the instant 0 plus. So at 0 plus, again, the exponential becomes just e to the 0, so that's 1. So we just have a negative sigma out front here. And then again, the sine of 0 is 0. The cosine of 0 is 1. So we're just left with e to the negative sigma times a1, basically, for those first two terms. So that's here. Although, it turns out, remember, a1 is actually 0, so that term's actually going to go away entirely. Then for these next two terms, again, the exponential becomes e to the 0, that's 1. And then here the sine becomes 0 because it's sine of 0. And then the cosine of 0 becomes 1. And so we just end up with basically omega d a2 is all we're left with. And then remember that we found that that was equal, in the analysis we did of the first derivative circuit, we found that that was equal to negative 0.1176 volts per second. So that's the value of V naught of 0 plus, so we put that in here. And then we know omega d, we've already computed that. That was up here, 0.2669 radian per second. So we just plug that in here, and then we can divide to find A2. So the algebra is very simple in this case, just this divided by this. And that gives us a negative 0.4409 volts. The seconds, inverse seconds are going to cancel out there in the numerator and denominator, just giving us volts, which is the proper unit for A2. Okay, so now we did want to finally put it into this form, which is basically uses the difference identity for cosine. And when that's applied here, and that can also be written in terms of, instead of sigma, we can use sigma being 1 over tau. So that's how I rewrote it here. And we do have to keep that particular solution again. Don't forget that. And the identity, and that's given to us here, is that A is going to be the square root of A1 squared plus A2 squared. Well, that's pretty simple here because A1 is 0 and A2 is that negative 0.4409 volts, and we square that, take its square root, which of course just gives us the absolute value of this number, which is the 0.4409 volts, okay, without the minus sign now. So that's the amplitude. Remember, that always has to be a positive number. As you can see from the way it's constructed, it's always going to be positive because A1 and A2 have to be real numbers. Okay, so that gives us the number to put in for this prefactor is 0.4409. And then the units here have to be volts, of course, because this is a voltage that we're calculating. So instead of amp or watt, we put in the volt there. And that term can be used for any of those different types of transients. That's why it has that. And then the time constant in the e to the negative t over tau, we computed that now as 68 seconds. So we'll put in 68 seconds there. And then our omega d is the argument here. This is going to be cosine of omega d t minus phi. So the omega d, remember, was the 0.2669. So we put that in there, 0.2669. And then our phi, that's the last thing to calculate. That's the inverse tangent, basically. Since the a1 is 0, we just use basically this formula here. This is the atan2 function, but in this case, we just use this form of it. So it's inverse tangent of the a2, which is the negative, and the sign matters here, 0.4409 divided by 0. So that gives us negative infinity as opposed to positive infinity. And that's important, of course, because the inverse tangent of negative infinity is negative 90 degrees. Remember, if you draw the unit circle, that's where the cosine goes to 0, and the sine would be negative 1. So that's why it gives us the negative 90. Okay, so that's, since it's minus phi, we put negative 90 in there. Okay, and that's our formula. And so now we just have to check that equation. And that was correct. And it's just going to redraw things here in a moment. Okay, so we have the equation now that we entered correctly. Basically that's all we need to do, so we can click no more equations. Now, we do have the option of viewing a detailed explanation. If you were unsure about any part of this calculation, you can say yes. And then you'd have this interface again where you can choose, maybe you just wanted to see, you weren't sure about what happened at t equals infinity, or maybe you wanted to see several of these. You can do whatever you want and look at whatever level of detail you like and plot that. And I'm going to skip that for right now. But basically, we are done.